Here we go. Let's get into some of the motor calcs. First one that popped up was number 1 on your side. That is number 11. Let's just go through it. Let's talk through the entire thing. So hopefully we can make a little bit of sense of it. If you're struggling with these at all, I'll kind of limit the amount that I talk about it as we go. But for the sake of saking, let's get it popping. Refer to the nameplate shown in figure 230.122. The branch circuit for the motor is supplied from a 120, 240 volt, 3-phase, 4-wire panel board. What is the minimum size, 3-wire plus ground, SO cord that can be used as a flexible connection to the motor? First thing I want to point out is that we are using SO cord. SO cord does not size out of 310.16 like the rest of our conductors. Okay, we've talked about this briefly, but SO must be sized out of table 400.5. Okay, flexible cords and cables are going to size out of here. And remember, it's that A column, B column, 3 conductors versus 2 conductors in use. Okay, so we'll take a look at that in a second. That's the first point. Next point, when you're doing one like this, is we want to make a couple considerations. Just because we have a 3-phase system does not necessarily mean we have a 3-phase motor. So we want to verify that when we come into any of these. And you'll usually see that somewhere in the question. And if they posted a nameplate, you'll definitely see it in the nameplate. So that is going to be important that we differentiate single phase and 3-phase when we're looking up the FLCs in the code book. Okay, the next most important thing is going to be the horsepower rating of the motor. In this case, I'm looking at a 7.5 horsepower. It is going to be 240 volt, 3-phase. Okay, once I have those bits of information, I can hop into the code and do a little work. Okay, so for the code or the charts in the back, we will call it FLC, full load charts. Okay, when we're using these, we're going to use those to size the conductors, and we are going to use those to size the overcurrent protective device. Okay, the nameplate is only used for one little thing. There are some other circumstances where you might use it if it's like fire pumps or something like that, but realistically, the nameplate's only going to be used for overloads. Okay, everything else needs to be sized out of the tables in the back of the book. And remember our reasoning behind it. Okay, there's your overload portion down there at the bottom. That's going to be sized off the nameplate. Okay, and we use those charts in the back because they give us a little bit of flexibility. Right? We don't want to be stuck at the edge of one size wire or one size overcurrent protective device because maintenance had to switch out the motor a couple years down the line. So the charts in the back of the book, 432.48, 432.50, they're going to give us a little bit of buffer. Okay, to account for different voltages that may or may not be present at your job site, as well as different manufacturers' specifications on their motors. Okay, so it gives us that buffer. It's built into the table, so that way a simple motor swap won't turn into an entire circuit upgrade. Is kind of the concept. Okay, so now that we talked through that, let's go look at the charts. We're talking 3-phase, 7.5 horsepower. Let's jump into the NEC and head to the back. 440, and then I'm going to roll backwards to 430.250, and that's going to be the full load current for 3-phase alternating current motors. Now, do remember down here, it's going to give you a little bit of information about the nominal ranges on some of these voltage systems, and you might occasionally even see numbers that are a little bit higher. It's going to specify, for instance, 220 to 240, but sometimes you might see 245. You might see 250. Same with that 440 to 480. A lot of times at some of the plants and factories we work out, we come in a little bit closer to 485 in some of ours. So they still fall within those variance ranges that you see there. Okay, for this particular one, we're talking a 7.5 horsepower, and we have to just verify that voltage again. It was 240 volt according to the question. So 7.5 horsepower, I will go out of the 230 volt column. Okay, that's our nominal. And my FLA is going to be, or FLC I should say, is going to be 22 amperes. Okay, so let's write that down, 22 amps. Now, the next most important thing. Unless the question or the apparatus specifically says that it's intermittent duty, we are just always going to apply continuous to all of these. So we must use that 1.25 multiplier when we're doing these. So just take that 22 amps times 1.25. Let me pop up a calculator and let's do it. 22 times 1.25 equals 27.5. Okay, so always continuous unless the question specifically says not to do that. Okay, you just always do it. Just do it. Just do it. Just do it. So 27.5 amps is the conductor I am going to be looking for here. So we, since are using SO, we're going to head to table 400.5 and find us a conductoid that is going to be good for this circumstance and situation. 400 flexible cords and cables. I'm going to cruise on down to 400.5 for our ampacity. Okay, we have two columns inside of table 400.5, and just remember which one to use. In this one, I believe it is subnote 1, column A. Says the currents under column A apply to 3 conductor cords and other multi-conductor cords connected to utilization equipment, so that only 3 conductors are current carrying. Okay, that's going to apply to our situation here. So we're just going to cruise right on down and find us a conductor that can handle that 27.5 amps. Looks like 29 is a number 9. Yep, number 9. It exists. Okay. Now, whether the supply house actually carries it or not is probably the question, but for calculation purposes, number 9 is going to be the one. Okay, so that's how you size that all out. We put in that number 9 and we call it a day.